This is example 12-7, the critical depth for flow rate. So we have this trapezoidal channel here. And we know that we need to transport 12 cubic meters per second of water. And we're asked to find the critical depth and the critical slope. And we're given the surface roughness coefficient. All right, so for that, we have our equation, right, that relates the flow rate. Q squared over G to our critical flow area. The third power divided by B top. All right, Q is given to us. And of course, AC would be how much water there is that's flowing across here. It's the cross-sectional area. And B top would be the height, right? So basically we're trying to find if this would be our critical depth, all right? So we're trying to find this. YC, of course, in this case, this distance would be B top, all right? So area is just the area of a trapezoid. I think what we're going to do is we're going to use the standard area, but we need to figure out what we're given the angle. So we just need to kind of figure out what kind of these little extra parts are, right? So if we kind of think about this as triangle here, a triangle there, right? Then we can say this, we call this little part C, right? Then we know if we have the angle here, then we have the same angle. We have the angle not going all the way through, of course. We have the angle here, right? Then we have the same angle there. We call that angle alpha, right? Then we can say that we know what the height here is YC, the other one is C, so we can say the tangent of alpha is equal to the YC over C. All right, the opposite leg over the adjacent leg that we have there. We can solve that for C because that's what we're looking for. So C is YC over tangent of alpha. In our case, we know what the alpha is, so it'll be YC over tangent of 60 degrees. And of course, we know what that is, so we can just say YC divided by square root of 3. All right, so that is that little chunk there. So that means we can say that B top, all right, is then just C times 2 plus the width here, right? Let's call that B. So that would be B plus 2 times C, or B plus 2 times YC over square root of 3. All right, so we have our B top. That means now we can also figure out what our AC is. For that, we take the equation from the book, all right? So we know that that would just going to be YC times YC over tangent alpha plus B. And in our case, again, because we know what alpha is, we can plug that in. So we'd have YC times YC over square root of 3 plus B. All right, that's our AC. Now if we have AC and we have B top, right, then we can plug those in. So we can say Q squared over G, that was AC to the third power. So that'd be YC over square root of 3 plus B, all that raised to the third power, divided by, and then b top was b plus 2 times yc over square root of 3. And basically now all we have to do is we have to solve this for yc, because our yc is going to be the only unknown. We know what the flow rate is. We of course know what the gravity is, and then yc is what we're looking for, and b is we already know. Right, so that means we can solve all this for yc. So let's go ahead and do that. I'm not sure can I fit up here. No, let's give it some space. All right, so we say that is equal to, and now if we break this one up, right, then we have yc to the third power times, and now this first one to the third power, so it would be yc to the third power divided by 3 times square root of 3. And then we just have to use the regular formula, right? Plus 3 times a squared times b. So that would be yc, not y to the c, that would make it more difficult. Yc squared over 3 times b plus 3 times ab squared, so it'd be yc over square root of 3 times b squared, and then b to the third power. And that all still divided by b plus 2 times yc over the root of square root of 3. All right, I think we can simplify this just a little bit. So let's leave the yc to the third power right here. The first one we can't do very much about. So that would be yc to the third power 3 times square root of 3. Here the 3's cancel out, so b times yc squared plus, now if we multiply this fraction by square root of 3, right, then that would, we'd have square root of 3, square root of 3, so that would be 3, those cancel out, so we just have, we'd have b squared square root of 3 times yc, and of course the last term there's not much to simplify. And all that still divided by b plus 2 times yc square root of 3. All right, so if we want to solve this, we'll have to get the yc out from the bottom there. So we can multiply this whole thing, so we'd have q squared over g times b plus 2 times yc over square root of 3 equal to all this, but let's break this one apart first because this has a yc in there too. So that would be equal to q squared times b over g, that's the first one, plus 2 times q squared over square root of 3 times, I'm using a g, times yc, just yc. All right, and that is equal to all the rest here, and we'll pull in the one out here, so we'd have 1 over 3 times square root of 3 yc to the 6th power plus b times yc to the 5th power plus b squared square root of 3 times yc to the 4th power plus b cubed times yc to the 3rd power. All right. Now what else can we do? I guess we can bring all the terms on one side so we can have equal to 0. And I think that's all we can basically do. Then we'll stick in some numbers. So our highest term would be 1 over 3 square root of 3 yc to the 6 plus b times yc to the 5 plus b squared square root of 3 yc to the 4th. Oops. Plus b to the 3rd times yc to the 3rd. That was all on one side. Then on the other side we have, so we don't have a square term. So the next one would be plus 2 times q squared over g times square root of 3 times yc. And then we have a constant. Oop, those are all minuses. Before I make sure, right? Because we're bringing them over from the other side. So that'd be a minus here. Minus, where's my other term? Q squared times b over g, and that is, sneak it here in the bottom, equal to 0. Right, so that would be our entire equation. Right, so we have a 6th order polynomial that we need to solve. To do that, we need to plug in some numbers. So that's, before we plug in numbers, let's think about units for a second here, right? So this would be the 6th power. A length of the 6th power would be our first term. Our second term, we have y is going to be a length, so length to the 5th plus another length, length to the 6th. Here again, we have length of squared, length 4th. Length 3rd, so that's also 6. And then back here, gets a little more complicated. We have cubic meters per second, divided it by, cubic, so it would be length to the 6, divided by 1 length to the 6, length to the 5th, and then times 1 length to the 6th, and we have square sets. Okay, that one works out, and the last one works out as well, because all we're doing is the Q, C, and the B get replaced. All right, so unit-wise, I think we're looking good. Now let's stick on the numbers. Nothing at the first one. It's just a constant. YC to the 6th. Now the width of our channel is, no, that's not the width of the channel, it's the width of the bottom here, B. That was 3 meters. So that would be 3 meters times yc to the 5th. Then we have, let's put the square root on front here, times 3 meters squared times yc to the 4th plus 3 meters to the 3rd power yc to the 3rd minus 2 times our flow rate, 12 cubic meters per second, times 12 cubic meters per second squared divided by 9.81 meters per second squared times times the power at the square root of 3, there we go, times yc, and then the last one we're going to stick down here, minus 12 cubic meters per second squared times width is still 3 meters at the bottom, divided by 9.81 meters per second squared, equal to 0. All right, then we can stick all this into a calculator and get the actual numbers. So I would get 0.19245 times yc to the 6th power. The next one's easy. 3 meters times yc to the 5th plus 15.588 0.46 meters squared times yc to the fourth plus 27 meters cubed times yc to the third. Again, we don't have the square term, so then we get the linear term, 16.9497 meters to the fifth times yc, and then minus our constant, 44.0367 meters to the sixth. And all that, of course, has to be equal to 0. Very good. So we can plug that into any kind of a calculator, or again, I like to use Python. When we do that, we'll see that, of course, we get 6 solutions because it's 6-order polynomial. But we can see that all except one of the solutions are complex. So, of course, that doesn't work for us. The only one that's not complex, the only one that's real, is the one that is the right one for us because it's a physical problem. So we get that the critical depth, yc, is equal to 1.09328 meters. Or if we round, 1.09 meters. All right, so that was our critical depth, right, that we get. Now the question is also, what is the critical slope? So for that, we can take our slope formula, right, our critical slope. We know that is SC is equal to n squared times G times AC divided by B top times the hydraulic radius, it's critical, raised to the 4/3 power. Right? That's when it gets kind of tricky up there with the weird exponents. All right, so what we can, of course, we can just plug in numbers right away, but I think we'll calculate the AC, the B top, and the RHC separately, and then plug them in to make it a little less complicated. So if you remember, the RHC was just the AC divided by PC. So let's start with calculating AC. AC is equal to, as we figured out before, YC times YC divided by square root of 3 plus B. That would be, we just found out, 1.09328 meters times 1.9328 meters divided by square root of 3 plus B, which was 3 meters. And that gave me 3.96992 meters squared. Now we can go back and look up what the wetted perimeter for trapezoidal cross section is, and so we found it's fine. It's 2 times YC divided by sine alpha plus B. So in our case, that is 2 times 1.9328 meters divided by sine of 60 degrees plus 3 meters, and that is equal to 5.524822 meters. All right, so we have AC and PC, so it makes it easy to get the hydraulic radius. RHC is then just AC over PC, right? Because the hydraulic radius is just area over perimeter. So in our case, that is 3.96992 meters squared divided by, where we have it, 5.52482 2 meters. And that gives me 0.718561 meters. Well, radius should be a length. That looks good. And then the last thing, so now we have the AC and the RHC, so now we're just missing B top. But B top we also had a formula for, so we can say B top is equal to, or I said B times 2 times C, right? So it'd be 3 meters plus 2 times our YC, so 1.09328 meters divided by square root of 3, and that is 4.262411 meters. And with that, we can go back to our equation and plug everything in. Right, our equation up here. So we can say that will be, well, let's just write it down one more time. Right, n squared times g times AC divided by b top times RHC to the 4/3. And that is equal to, well, we're given the 0.014. So that's 0.014. Now, the units of this is a little strange, but we'll put them in so that we can check our units. So it's second over meters to the 1/3. And that's squared. 9.81 meters per second squared times 3.9699 meters squared, which was our area. We divide that by B top, which was 4.262411 meters. And then our hydraulic radius was 0.718561 meters. And that is to the 4/3. All right, let's look at units. Think about seconds. Right, we have seconds here, seconds squared cancel out. Good, because we want to have a slope, it won't have a unit. Right, or basically, technically it's meters per meter, so meters cancel out. Now, how about our meters? We have on top, we have meters to the 3rd, right? Meters and meters squared. Then at the bottom, we'd have meters to the 1st, meters to the 4/3, and here we have 2/3, so that'd be 6/3, that'd be 3, because 6 divided by 2 is 3. So overall, we will have our meters canceled out, so it's all good. So that means we get, if we put in the numbers in the calculator, 0.00278 or 2.78 times 10 to the minus 3. That would be our critical slope. And we also calculated what the critical depth was. And so with that, we have answered all the questions for example 12.7.